Now let us consider the boundary layer on a flat plate. The first problem on boundary layer, which was solved by a student of Prandtl by the name Blasius, a fluid dynamist of great repute by himself. For a flat plate, the continuity equation is del u by del x plus del v by del y is equal to 0, and the x momentum equation within the boundary layer is rho times u del u by del x plus v del u by del y is equal to minus dp by dx plus mu del square u by del y square. We have dropped mu del square u by del x square because of the properties of the boundary layer. That is, only in the y direction the viscous stresses are significant. The x direction gradient del square u by del x square times mu is insignificant. And this is to be solved with the boundary conditions that u and v, the velocities at the boundary y is equal to 0, should be 0, and that u tends to ux asymptotically as y tends to infinity. dp by dx, of course, is 0, flat plate, low pressure gradient, and this gives you capital U as constant. Those who are versed in the theory of partial differential equations would notice that this equation is parabolic partial differential equations and can be solved by using a starting solution at x is equal to 0 and then marching along x. The solution of at x is equal to 0 is that the horizontal component of velocity is equal to v naught or capital U everywhere, so that we can march from there onwards. The marching means that after the solution x is equal to 0, we go a little distance in the x direction and find out the profile there. But an interesting thing to notice in this boundary layer on flat plate is that there is no characteristic length in the x direction. We start from x equal to 0. This plate extends to infinity. So there is no characterizing length, and that's why the velocity profiles at different values of x should be similar in certain sense. In the sense that if we take velocity profile at one station, we can scale it properly to fit at any other station. These are known as self-similar solutions. Profile at one x is similar to profile at another x. So in this picture, velocity profile at another x can be obtained by simply scaling the velocity profile at the first value of x. We have compressed this profile in the vertical direction to adjust for the value of delta there. The only difference between the two profiles is that the extent of the variations in the profile is now smaller. Delta is smaller at the first location than at the second location. We could scale it further and obtain the velocity profile at the third location. I drew these second and third profile simply by changing the scale in the vertical direction. In the horizontal direction, the scale is same because the velocity at the edge of boundary layer is the same. These are, as I stated before, known as self-similar solution. So in these cases, we can treat as if there is only one variable, space variable, and that u by capital U is a function only of y divided by delta c. There is no x dependence except that the delta c is a function of x. But if we use delta c appropriate for a given location x, then the u by u, the capital U, becomes a function independent of x with delta like x divided by under root Reynolds number based on x. Y by delta c becomes y into square root of capital U divided by nu x, and we call it eta. So eta is now a composite variable that varies like y over root x. On introducing the stream function psi, the continuity equation can be automatically satisfied, and one can show that by defining psi is equal to under root nu x capital U times f of eta, that function f of eta, we get u by capital U as f prime of y over delta c. That is f prime of eta, where f prime stands for del f by del eta. And the x momentum equation becomes simply an ordinary differential equation of third order, f double prime plus twice f triple prime is equal to 0. To be solved with the boundary condition that f is equal to 0, this is because the surface itself is a streamline, f is equal to 0 and eta is equal to 0, and f prime is 0 and eta is equal to 0. F prime is like u, the horizontal component of velocity should be 0, no slip condition. F, the no slip condition, and the fact that the surface of the flat plate is impermeable gives you f is equal to f prime is equal to 0 and eta is equal to 0. And the far away boundary condition becomes f prime tends to 1. That's lowercase u divided by capital U is 1 as eta tends to infinity. This equation is rather easy to solve. A small MATLAB program we have been able to solve this. F prime is shown to vary like this blue curve, 0 at the wall and tending to 1 asymptotically as eta becomes large. The red curve shows the plot f double prime. F double prime relates to del u by del y. So f prime relates to u and f double prime relates to del u by del y, the gradient of velocity. You notice that the velocity approaches 1, the capital U velocity, very quickly, but almost never reaches 1. We arbitrarily define the boundary layer thickness delta as the location where the value of U divided by capital U is 0.99. That is, the streamwise velocity within the boundary layer is 99% of the inviscid velocity on the flat plate. We define as the boundary layer thickness. And so, this is obtained at eta is equal to 4.91, where f prime is 0.99. So, the boundary layer thickness is that value of y for which eta is 4.91. In classical literature, this value is normally taken as 5 instead of 4.91. This gives delta is equal to 4.91 x divided by Reynolds number based on x. Notice that the characteristic length across the boundary layer was taken as x divided by Reynolds number based on x. Another thing to note is the value of f double prime, which starts with the value of 0.332 at the wall. Remember, we said f double prime is related to del u by del y. And this value is 0.332 at the wall. We will use it to estimate the shear stress at the wall. These calculations are valid as long as the boundary layer flow is laminar, which on a flat plate is up to a Reynolds number of about 4 into 10 to the power 5. The shear stress tau W at the wall is mu del u by del y at y is equal to 0, that is at the wall, and which can be shown that with our transformation that becomes rho u square under root Rex times f double prime at wall. The value of f double prime at wall, that is at eta is equal to 0, was obtained at 0.332, and so the shear stress at the wall is 0.332 times rho capital U square divided by under root Rex. Rex increases as x increases, and so the shear stress decreases as we go along the plate. And the skin friction coefficient, which is defined as the shear stress at the wall divided by 1/2 rho u square, becomes 0.664 divided by under root Rex. The skin friction also decreases as x increases. The drag coefficient on the flat plate, defined as drag force on the plate of length L and depth B divided 1/2 rho capital U square times the area BL, can be obtained by integration. So that dF, the force contribution to the drag, is the shear stress times the area of a small strip of width B, that is of area B dx, and the total drag is obtained by integrating this from x is equal to 0 to L, the length of the plate. And using the expression for the shear stress that we obtained earlier, we get the drag coefficient as 1.3 28 divided by under root REL. Notice that for large Reynolds number, this drag coefficient still small. So it does not lead to D'Alembert's paradox. We have neglected friction, we have neglected viscosity effects, and the results that we obtain would be approximate. The error that we should be contributing should be of the order of viscous effects, and since viscous effects are small, the error should be small. We predict a drag of 0 and we obtain a drag which is like 1 over under root Reynolds number for large Reynolds number. So there is no paradox involved here. The drag is small. The paradox arises on bluff bodies, where though the prediction from inviscid theory applicable for large Reynolds number is still the drag should be 0, but the drag coefficient is of order 1. That is a paradox. How can the drag coefficient be that large? We will show later that it is because of the dynamics of this thin boundary layer due to Prandtl. And the dynamics leads to separation from the surface, where the boundary layer does not remain thin and the viscous effects penetrate in the main flow. Thank you very much.